On this example, we're given both sine and cosine for some angle t, and we're asked to find secant, cosecant, tangent, and cotangent of that same angle. So this shouldn't be too bad. What we're going to rely on as we go through this is we really need to know about reciprocal identities. All right, and to start out, we want to use that secant of t is the same thing as 1 over the cosine of t, based on this reciprocal identity. So what this boils down to is really just flipping the whole thing upside down, but I'm going to go through the steps to make sure we understand them. So it's going to be 1 over, now I'm going to fill in cosine of t, which was 1/2 from the given information. And we want to simplify, right? We don't want to leave a fraction within a fraction. So basically the idea is make this denominator equal 1. So we think to ourselves, 1/2 multiplied by 2 is going to give us a 1 there. But if we want to multiply the denominator by 2, we also have to multiply the numerator by 2, so that 2 over 2, you're multiplying by 1. All right, so multiplying straight across, numerator multiplied by numerator, 1 times 2 makes 2. Denominator multiplied by denominator, we kind of plan this out that it's going to be 1. All right, so 2 over 1 is going to be our secant of t. Or simplify, 2 over 1 is the same thing as 2. All right, what I want to point out is I went through all the steps there, but really if we started out with 1 over 2, the reciprocal simply states that we have to flip this upside down. The reciprocal would be invert numerator and denominator and get to 2 over 1. So with that in mind, we can make this a faster process if we wanted to get cosecant of t. Cosecant of t, though, is 1 over sine of t from the reciprocal identity. Again, I'm going to go through our steps, but really you can flip-flop numerator and denominator, and you can get there pretty quickly. So we're going to go 1 over, now I'm filling in sine of t, which was negative square root of 3 over 2. Same thought process, we want to end up with no fraction remaining in our denominator. So I want to multiply the denominator here by 2, but to do so, I also have to multiply the numerator by 2. So multiplying by 2 over 2 is the same thing as multiplying by 1, which is going to work out pretty nicely. So here we get, 1 times 2 makes 2 in our numerator. In our denominator, we multiplied by 2 to counteract this dividing by 2. So we're going to be left with negative square root of 3 in our denominator. As you'll notice, if we just flip-flopped numerator and denominator from sine, we would get to the same spot. Let's talk real quickly about rationalizing this. I'm going to go ahead and move that negative out in front of the entire function instead of leaving it in the denominator. What we mean by rationalizing is we mean get rid of the radical from the denominator. So in this case, what we'd want to do is we'd want to multiply our denominator by the square root of 3 to do so. All right, so 2 times the square root of 3 makes 2 times square root of 3 in our numerator, but our denominator is going to work out to be square root of 3 times square root of 3, which is the square root of 9, which works out to be just 3. All right, so best answer we can get to there for our cosecant of t is negative 2 square root of 3, all divided by 3. All right, next up, tangent and cotangent. For tangent, what I'm going to rely on is a quotient identity, based on the information that's been given to us so far. So for tangent, the quotient identity that connects back to these other functions is tangent is equal to sine over cosine. So from here, I'm going to take that given information from the beginning and fill in. So we have negative square root of 3 over 2 for our numerator, right? That's replacing the sine of t. And then cosine can be replaced with 1/2 from the original information. Again, we don't want to leave it with fractions inside of fractions. So I want to multiply by 2 over 2 to counteract those dividing by 2's and the little fractions on the inside. So multiplying by 2, dividing by 2, multiplying by 2, dividing by 2. What we're going to be left with in this case is going to be, well, we have negative square root of 3 in our numerator. We'll end up with a 1 in our denominator, which is really, right, we can get rid of the 1, say that's really just negative square root of 3. All right, next up, cotangent, the last one we have to get to. You could think of this as being a reciprocal identity. All right, reciprocal identity would say that cotangent is connected with tangent in a reciprocal relationship, that it's 1 over tangent. So with that in mind, we can really just go back to, let's use this version of it, of tangent, and fill in. All right. You can fill in by simply flipping this upside down, or you could use this last version maybe to fill in, be the cleanest. Let's use that last version. I've changed my mind. So negative square root of 3 gets filled in for tangent. Then what we want to do is clean this up a little bit, rationalize our denominator. We could multiply numerator and denominator both by square root of 3. And this should give us, I'm moving the negative out in front. 1 times square root of 3 makes square root of 3. And then square root of 3 times square root of 3 is square root of 9 in our denominator, which will simplify a little bit. Your alternative to this would have been utilizing a quotient identity to find cotangent. The quotient identity we could have relied on would have been cosine over sine. Probably be the easiest one to remember that I would utilize. We get to the exact same answer, whichever versions you use. So just make sure you're clear on which you're utilizing. And I tried to show all my work throughout this where I was filling everything in, not just flip-flopping numerator and denominator. Typically, if I were doing this on my own, I would have just flip-flopped numerator and denominator and made this as quick and painless of a process as possible. But I hope this helps out as you see some different ways to show your work, how to utilize the reciprocal and quotient identities to get all of our trig ratios. Good luck.